Hi everyone, welcome to Unit 4 of online course on probability distributions. In the last 3 modules, we have discussed basic concepts with respect to random experiment, sample space, events, random variables, distribution functions, probability density functions, and mathematical expectations and some symbol properties. Also, we discussed 2 preliminary distributions that are known as degenerate distribution and discrete uniform distribution in the last module. Now, we are moving to discuss important distributions such as binomial distributions, Poisson distribution, geometric distribution, negative binomial distribution, etc. in the case of discrete random variables. And again, in the case of continuous random variable, we are going to discuss exponential distribution, gamma distribution, beta distributions, normal distributions, etc., and their applications and characterizations. And here we are going to discuss binomial distributions. Before introducing the binomial distribution, let me give an introduction to Bernoulli distribution. What do you mean by Bernoulli distribution? Suppose we are performing a random experiment whose outcome can be classified as either a success or as a failure with a probability of success p and a probability of failure 1 minus p, or let it be q. Such trials we call it as Bernoulli trials. For example, suppose we are tossing a coin, then the outcomes are head or tail. So, it may be termed as success or failure with the probability of success 1 by 2 for the probability of getting head, and again 1 by 2 probability of getting tail. So, this is an example for a Bernoulli trial. Another example, suppose we are selecting items from a box containing defective and non-defective items. So, outcome may be defective with the probability q and may be non-defective with the probability p. So, that is a Bernoulli trial. Suppose we are noticing the sex of a newborn child, then it may be male or female with the probability of success p and probability of failure q. So, such situations arise in our in the case of experiments. So, that Bernoulli, corresponding to that Bernoulli trial, we are discussing a distribution that is known as Bernoulli distribution. So, we consider Bernoulli distribution, and suppose you are considering a random variable, a discrete random variable of course. So, define the random variable x, and that x is a random variable. Suppose you define a random variable x, and that random variable is equal to having only 2 values. Let it be 0 if the outcome is a failure, let it be fail, the outcome is failure, and 1 if the outcome is a success. So, a Bernoulli trial we are considering so that in the Bernoulli trial only 2 possibilities, it may be either success or may be failure. And let p be the probability of getting success we denote, and q is the probability of failure, and q is of course 1 minus p. So, this is a Bernoulli random variable, and this Bernoulli random variable, the distribution function of this Bernoulli random variable. So, this x is called Bernoulli random variable, and corresponding distribution is called Bernoulli distribution. So what is the Bernoulli distribution density function? Probability mass function. Probability mass function or probability density function of discrete random variable in the case of Bernoulli random variable. Already given that the random variable have the values 0 and 1, so probability of x is equal to 0, that means probability of getting failure, and that is denoted by q, and probability of x is equal to 1, that is probability of getting success q. This is our probability mass function. So if you are making that in a table form, so x have the value 0, 1 and f of x value is equal to q and p. Or generally we can write this as in the function form as p power x into 1 minus p or q, or let me generally write 1 minus p or power 1 minus x, that x is equal to having the value 0 and 1. So this is the probability mass function of the Bernoulli random variable. When x is equal to 0, this value is 1 minus p, that is q, and when x is equal to 1, this value is p. So this is the Bernoulli distribution. This is the most simplest discrete distribution. While we are discussing the Bernoulli trials, we are getting this distribution. And what is the mean and variance of this distribution? So when we are going to find the mean and variance of the distribution. So this is the Bernoulli random variable are used to model experiments that have two possible outcomes, already I mentioned. And Bernoulli distribution arise anytime we have a response variable that takes only two possible values, and let it be denoted by 1 and 0 or whatever be the values. So two possible values, and in such case Bernoulli distribution arises. So probability mass function already I have given that probability mass function is equal to probability of x is equal to 1 is p and probability of x is equal to 0 is 1 minus p. So the generally function in the function form you can write the probability mass function as p power x into 1 minus p or power 1 minus x. Now what we are finding the expectation of x and variance of x. So what you have the expectation of x, and by definition of expectation of x we have sigma over x, x into fx, and we have only two values for x, that is 0 and corresponding f of x value is q, and 1 corresponding f of x value is p. So this is equal to p. So expectation of x mean is equal to p. Similarly expectation of x square, suppose you are finding, this is equal to, by definition of mathematical expectation of function of a random variable, it is x square into f. This is the way we are finding the expectation of x square, and that value is equal to again 0 square into q plus 1 square into p. So that is again p. So from this we can find the variance of x. By definition of variance, it is equal to expectation of x square minus expectation of x the whole square. This is equal to p minus p square, or that means p into 1 minus p, or by notation it is pq, because we have given q is equal to 1 minus p. So for the Bernoulli random variable or Bernoulli distribution, the basic quantities like expected mean and variance are p and pq respectively. So mean and variance are given by p and p into 1 minus p. Again, next quantity we are going to find here is moment generative function. What is the moment generative function of the Bernoulli random variable? Moment generative function, as discussed in the previous unit, we know mxt, that is moment generative function, is nothing but our expectation of e power tx. So this is our moment generative function, and that moment generative function is obtained by summation over x e power tx into fx. and we have two values for x and 1, x that is 0 and 1, that is e power t into 0, and the corresponding value of f(x) is q, plus e power t into 1, corresponding value of f(x) is p. So that means it is q plus p e raised to t. So for the Bernoulli random variable, the moment generated function is derived as q plus p e raised to t. So this is our moment generated function of the Bernoulli random variable. So mxt is equal to q plus p e raised to t. So this is the simple case. Before discussing the binomial distribution, we have a Bernoulli distribution that, and we are generalizing this case. Suppose we are performing n independent trials, n independent Bernoulli trials. So a Bernoulli trial that are independent, each of which results in success with the probability p and failure with the probability 1 minus p or q. So consider a sequence of n independent Bernoulli trials with the probability of success p and probability of failure 1 minus p. So such in the case of that Bernoulli sequence, our aim is actually finding probability of getting x successes out of n trials. Let me repeat. We are performing a Bernoulli sequence of n trials with the probability of success p and probability of failure 1 minus p or q. And we are interested to find what is the probability of getting x successes out of n trials. So that means we have a, so consider a Bernoulli sequence of n trials. So that means we have 1, 2, 3, etc. up to n trials are there, and each trial resulted either a success or failure. Success or failure. Then you count the number of successes out of n trials. Count the number of successes out of n trials. So it may be 0, no success at all, or it may be 1 success, or it may be 2 successes, etc. up to finally all are resulted in success, that is n successes. So suppose x is a random variable that is defined as number of successes obtained out of n trials of a Bernoulli sequence with the probability of success p. So this is a random variable, discrete random variable having the values 0, 1, 2, 3, etc. up to n. Then what is the probability mass function of this particular random variable? That particular random variable, we are finding the probability mass function. So see, outcome may be the combination of success and failure. So it is a sequence of success failures out of n trials. This may be this. How many successes and how many failures? There are x successes and n minus x failures. We are performing n trials, and out of n trials, assume there are x successes and n minus x failures. So what is the probability of getting such a sequence of outcome, one of such a sequence of outcome, that is S, F, S, etc. F, and the trials are independent. Trials are independent with the probability of success P and probability of failure 1 minus P or Q. This is equal to, this is P, 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 how many times? X times, and Q, Q, how many times? N minus X times. So, probability of getting this event, that is x successes and n minus x failures, is equal to the product of this p and q's, p x times and q n minus x times. That is, this is equal to p power x q power n minus x. Okay. Then this is one of the such situations. Out of n trials, x successes are possible in how many different ways? Out of n trials, x successes are possible in ncx different ways. ncx different ways. So, there may be ncx different combinations of successes and failures like this, and each combination has the probability p power x q power n minus x, and each of the combinations are mutually exclusive also. So, what is the probability of getting x successes, that is the random variable x, that is equal to x, that is random variable x is denoted as the number of successes obtained. So, probability of x is equal to x means probability of getting x successes and n minus x failures. That means this p power x q power n minus x is added ncx times. That means the value is equal to ncx p power x q power n minus x. So, this is the probability mass function of the binomial random variable. How we are deriving the binomial probability mass function? Let me repeat again. Consider random experiment of Bernoulli sequence of n trials with the probability of success p and probability of failure 1 minus p, or q, denoted by q. Then our aim is to find what is the probability of getting x successes out of n trials. Of course, if there are x successes, there will be n minus x failures. And what is the probability of getting one such sequence of sets of s and fs? That is equal to p power x q power n minus x. And out of n trials, x successes are possible in ncx different ways. So, total probability of x successes is the p power x q power n minus x is added ncx times. That is, probability of x is equal to x is ncx p power x q power n minus x. Of course, the value of x is equal to 0, 1, 2, etc. up to n, and p plus q is equal to 1. And this is known as binomial random variable or binomial distribution. So, that is the probability mass function. This is the way we are deriving the probability mass function of the binomial distribution. Probability of x is equal to x, that is fx is equal to ncx p power x q power n minus x, x is equal to 0, 1, 2, etc. up to n, and q is equal to 1 minus p. If x is a binomial random variable with the parameters n and p, if x is a binomial random variable with the parameters n and p, we shall represent it by x follows binomial with n and p. This n and p are known as the parameters of the distribution, and these parameters control the shape of the distribution. What will be the shape? Is it a positively skewed random variable, or positively skewed distribution, or negatively skewed distribution, or symmetrical distribution? That depends upon the value of the parameters, and that we will discuss in the next module. Okay. And again, one thing you can note, why this is f of x is our f of x is already we have the value ncx p power x q power n minus x, where x is any value from 0 to n. 0 to n. So, when x is equal to 0, when x is equal to 0, this value become q power n. When x is equal to 1, this value become nc1 p power 1 q power n minus 1. And n is equal to x is equal to n, this value become p power n. So that means this probability mass function values are actually successive terms of the binomial expansion of this q plus p all power n. So when you are expanding q plus p all power n, you will get the expansion as q power n plus nc1 p q power n minus 1 plus nc2 p square q power n minus 2 plus etc. up to p power n. And these are nothing but this value is the f of x value when x is equal to 0. This value is the f of x value when x is equal to 1. So binomial probability mass function values are the successive terms of the binomial expansion. So that is why this is known as binomial distribution. And also note that this sum, this if you are expressing this quantity, it is a sum of this value sigma x is equal to 0 to n and cx p power x q power n minus x, and that is naturally equal to 1 because it is a probability mass function, or you can see that q plus p is equal to 1. We have p plus q is equal to 1, so it is 1 power n. So this is 1. So this sigma over x is equal to n and cx p power q power n minus x is equal to 1. That concept we will use in order to derive the probability expectation of the binomial distributions in the next session. So before concluding this session, let us consider an example. Suppose a coin is tossed five times. So that means it is a Bernoulli trial of n is equal to 5, that is here n is equal to 5. And probability of getting success, suppose we are defining a random variable x as number of heads obtained So that means x can have the value 0, 1, 2, 3, 4, 5. And probability of getting success, that is probability of getting head, and that is equal to, we know it is equal to 1 by 2. So when a coin is tossing, getting head is equal, probability of getting head is equal to 1 by 2. So this is an example for a Bernoulli sequence of 5 trials with the probability of success 1 by 2. So that means our random variable x follows binomial with 5 and 1 by 2 as parameters. So let us suppose we are interested to find probability of getting x is equal to 3. What is the meaning of probability of x is equal to 3? X is equal to 3 means what is the probability of getting 3 heads out of 5 trials of a tossing of a coin. So that is obtained by, generally we know the binomial probability mass function is equal to ncx p power x q power n minus x. So here it is n is equal to 5, ncx here x is equal to 3, p that is 1 by 2, again 1 minus p that is q that is also 1 by 2. So 5 minus x. So that means it is 5c3 1 by 2 power 5. So that means the probability of getting 3 heads out of 5 tossing of a coin, 5 tosses of a coin is 5c3 1 by 2 power 5. Similarly, another example, suppose you are considering, suppose you are throwing a die. throwing a die some 10 times. And let us define the success as getting phase 1. So, this is the definition of success here. And so, what is the probability of getting success? Probability of getting success means probability of getting phase 1, that is equal to 1 divided by 6, because there are 6 cases, phase 1, phase 2, phase 3 up to phase 6. So, out of this only one favorable, that is 1 by 6. So, what is Q? The probability of getting failure, 1 minus 1 by 6, that is equal to 5 by 6. So, this is a binomial random variable x with n p, where n is equal to 10. We are throwing the die 10 times and p is equal to 1 by 6. So, f of x is equal to 10 c x p power x q power n minus x, that is 10 minus x. So, from here, if you are interested to find any probability, suppose what is the probability of getting 2 times phase 1. So, that is equal to 10 C 2 1 by 2 power 2, sorry 1 by 6 power 2, 5 by 6 power 8. Similarly, we can calculate any probabilities. So, these are the some examples of where we are applying binomial probability mass function to get the probability of interest. So, this we are winding up this session, and we will further discuss the moments and moment generative function and other characterization properties of the binomial distribution in the next module. So, thank you for hearing this.